Hey folks, welcome to the final topic in chapter 5. It's been a long chapter, kind of a grind, but that's okay. You're almost there and we're learning. Today we are, in this video anyways, we are going to look at the conservation of momentum, and we're going to talk about how that applies specifically to collisions. So we're going to look at things bashing into each other. People, cars, hockey players, what have you. Got a little note here that in a closed system, that simply means that you're keeping track of the objects before a collision, and you're also keeping track of the objects after the collision. So if we keep track of everything during a collision, we will always find that the total momentum, the initial momentum of all of the objects compared to the final momentum of all of the objects, it's totally constant. And that is always true. I may have shared this with you at some point in the course. I feel like I have, that school is kind of a series of white lies that are appropriate at the time. Like, you can't take 4 apples away from 3 apples. Well, you can. You can't take square roots of negative numbers. Well, it turns out you can. This is not something that we're going to throw back at you in Physics 12 and say, hey, remember in Physics 11 where we said momentum is always conserved? Well, it's not. It is. Every time. I can't think of an example where it's not. So, not a lie coming at you here. This is good, solid information that you'll be able to use from this point moving forwards. I want to show you an example of why this is true, or sort of proving how it's true. So, here's what we're going to do. We're going to look at a collision, and we're going to talk about what happens before, what happens during, and what happens after. And remember, this discussion is all about the momentum before, during, and after. So before a collision, we've got an object who's, or maybe a person, who's 80 kilograms. Let's go with people. 80 kilograms running at 10 meters per second is going to catch and bump into somebody who's 20 kilograms moving at 4 meters per second. So if we go and calculate the initial momentums for both of those people, momentum, remember, is simply m times v. So the initial momentum is, I should put units on here, for this first object is positive 800 kilogram meters per second, 80 times 10. And for the green object, it's 80, 20 times 4. And again, we should probably put some units on that, kilogram meters per second. So that means in total, before the collision, we have an initial momentum total that is equal to 800 plus 80. We have 880 kilogram meters per second worth of momentum between the two people. Now, that's when the 80 kilogram person is closing in on the 20 kilogram person. Let's imagine they actually make contact. So what about during the collision? During the collision, what's going to happen is this 80 kilogram object is going to bang into the 20 kilogram object. And when it does that, it is going to deliver a force. It is going to push on that smaller object. So really what we have here is we have an impulse being delivered to this smaller object. And let's say that the impulse is, I don't know, let's go with 100 newtons for 2 seconds. So a nice big crash, maybe it's like a big sibling pushing a little sibling or something like that, nice big shove, 100 newtons for 2 seconds. So that means there has been an impulse delivered here, and that impulse is F times t, 100 times 2 seconds. There's an impulse of 200 Newton seconds being delivered to the 20 kilogram person. Now there's a bit more to this story. I want you to think about Newton's laws. Newton's third law is all about action-reaction forces. And maybe as I mention that, you're going, oh, I kind of know what's going to happen. If the 80 kilogram person pushes on the 20 kilogram person, pushes on their back with 100 newtons for 2 seconds, that means that technically the 20 kilogram person is pushing back on the 80 kilogram person with an equal but opposite force. So there's actually this negative 100 newtons acting on this person for 2 seconds. Action-reaction forces, right? They're always present. So it turns out we have an impulse acting on the 80 kilogram person. It's backwards, so I'm going to include that negative sign. It's negative 200 newton seconds. Now, keep in mind that impulse is the same as change in momentum. So this impulse on the smaller person of positive 200 newton seconds, that's just as good as saying, hey, we added 200 kilogram meters per second worth of momentum to that person. So you can actually almost think about it like that. Hey, we've added 200 kgms, kilogram meters per second to that person. And for the 80 kilogram person, they had this negative 200 newton second impulse act on them. That's like saying, well, we took away 200 kilogram meters per second worth of momentum. So really all that's happened here is the 80 kilogram person has donated or transferred 200 kilogram meters per second of their momentum to the smaller object. They've given it up. We've simply taken a chunk of impulse or a chunk of momentum. The two things are exactly the same. We took it from the 80 kilogram person and we simply gave it to the 20 kilogram person. Which means if we go back to that picture that I showed last video of Nakai Penny smashing that kid on the rugby field, and I had sort of pointed out the poor kid's face, he was feeling that momentum. All Nakai was doing, let's put a positive spin on things, all Nakai was doing was donating some momentum to that kid. Right? Here, take some of my momentum via an impulse, because impulse is momentum. I would like you to have some of my momentum. It was a gift to that other young man. So that's the during the collision, and I'm just going to keep inking this by hand. What about after the collision? So we've had this transfer of momentum now to the 20 kilogram object. So this 20 kilogram object initially had 80 kgms of momentum. Now we've got this additional 200 newton seconds, which is the same as an additional 200 kilogram meters per second worth of momentum. So now this 20 kilogram person, they have a final momentum of 280 kgms. And since their mass is 20 kilograms, we can really quickly go and solve for their change in velocity. Remember, if you have a change in momentum, that's going to change your velocity. It's not going to change your mass. Let's imagine this 20 kilogram person didn't lose a limb or something like that, massive blood loss. So 280 kilogram meters per second, if we divide by the mass to get the velocity, that I believe gives us a velocity of 14 meters per second. That's fast, right? That's really fast. That person probably can't run 14 meters per second, so now maybe they're flying like Superman through the air. They might be doing one of these, heading that way. Now, what about the 80 kilogram person? They started with 800 kilogram meters per second worth of momentum, but they've lost 200. They made a donation to the smaller person. So this person is still moving forwards because they still have positive momentum, but they're 200 kilogram meters per second short of what they started with. So their final momentum is now down to 600 kgms. And if you divide by the mass, 600 divided by m, we're solving for v. I think that's 3/4. So 7.5 meters per second. Now the big takeaway here is that we started, this has disappeared, but we said the initial momentum in total was 880 kilogram meters per second. And now if you look after the collision, PF total, the final momentum in total is 880 kilogram meters per second. So during a collision, all that's going to happen is one object is going to give up or donate some of its momentum to the other object. Now the good news is this is looking kind of busy now, and I apologize for that, to squeeze it all on one screen. It turns out we don't have to go through collision questions like this. There's a much shorter way of getting to something like these final velocities, and let me show you what that looks like. So here's the equation based on this collision. And sometimes when I flash this up on the screen, students look at it and they go, holy smokes, Heinrich, like that's long. There's a ton going on there. But I want you to look at where those numbers came from, because it actually turns out that it's really, really straightforward. The 80 times the 10, that is simply our mass number 1, the mass of person 1, multiplied by their initial velocity. So that is an initial momentum for the 80 kilogram person. The 20 and the 4, well, that's simply mass number 2 multiplied by that object's initial momentum. Initial velocity. Which means when we multiply those two things together, that is simply the initial momentum for mass number 2. And we add those two things together and we say, well, it has to be equal to, we're back to mass 1 multiplied by its final velocity, the final momentum for mass 1, plus the final momentum for mass 2, m2 times its VF. So really all we're saying here is if you want to find something in this equation, you simply add the initial momentums of the objects, you set it equal to the final momentums of the objects. You know those two things have to be the same. We had said it was 880 equals 880. And in the questions that I give you in Physics 11, I am simply going to withhold one of those probably velocities. I'll give you everything else and you simply need to solve for the one unknown velocity. So on your formula sheet, here's what it's going to look like. Let me just erase this stuff here. This is what it looks like on your formula sheet. Some kind of cool new symbols here. So these cool looking little sort of E's are sigma. And sigma means the sum of. So you add together. So that says add together all the initial momentums, and that will always be equal to the sum of adding together all the final momentums. So that's what you'll find on the formula sheet. Some students will look at that and they'll go, well, Heinrich, why do you give us this like crazy sigma pi equals sigma pf? Why don't you just give us that equation? And it turns out that equation is only true if there are two objects colliding. But what if there were like 3 objects involved in the collision, right? What if 3 things all came together before and after the collision? And it turns out it's really, really easy. If there were a 3rd object involved in the collision, we would simply add a 3rd momentum. We would say, hey, m3 times its initial velocity and m3 times its final velocity. So because you could have any number of objects colliding together, I can't really give you this top equation with just 2 or just 3. Instead, we just say, hey, the initial momentums of all the objects before equal the final momentum of all the objects after the collision. We don't even worry about that impulse piece in the middle. The math is just going to sort that out. So let's try a couple of examples here where I will show you what it looks like to sort of withhold one of those velocities and go find it. I think you'll like these. These are pretty darn easy and most students have awesome success with these. All right, let's try. I actually just have 2 examples for you. This lesson's a bit shorter. Let's find the final velocity of a 20 kilogram ball. You can see here that before the collision, we've actually got a head-on collision happening here. A 30 kilogram ball moving at 8 meters per second. It's going to smash into a 20 kilogram ball moving to the left at 10 meters per second. And then I've called this after number 1 because what I'm going to do is actually work with the same before the collision scenario, but then just change up the next example, change up what happens after the collision. So we'll call this the after the collision scenario 1. We can see we've got the 30 kilogram object bouncing back to the left at 5 meters per second after this head-on collision, and we want to know the final velocity for that 20 kilogram ball. Now, there is something you have to be careful of with these collision questions, and hopefully you're looking at this before scenario and actually even the after scenario, and maybe you're going to see it. The big difference with this collision compared to the first one that we went over together is that this is a head-on collision. It's not one object just kind of catching up to another. So we have to make sure that when we go and we plug velocities in, that we tell the equation that this is a head-on collision. That means that anything going to the left has to be negative. So you have to catch that the 20 kilogram object going left at 10 meters per second, that has to go in as a negative 10. And then this 30 kilogram mass after the collision, it's going left at 5 meters per second. That's negative 5 meters per second. So you have to remember that left equals negative. So make sure you catch that when you're going to plug the velocities in. That is one of the only times that students make mistakes, is they forget that little note. Left equals negative. So on your formula sheet, if you want to go sort of hunting for things, all you're going to find is this. Sigma pi equals sigma pf. The sum of the initial momentums equals the sum of the final momentums. It's really not that bad. Let's run through the before. We've got a 30 kilogram mass traveling at positive 8 meters per second, m times v, plus we've got a 20 kilogram mass traveling to the left, negative 10 meters per second, m times v. We set that equal to, that is the initial momentums. We set it equal to the final momentums. We've now got a 30 kilogram object traveling to the left, which is negative, at 5 meters per second. There's a final momentum. And we've got this 20 kilogram object multiplied by some unknown velocity. So you can see now algebraically it's pretty darn nice. This is like grade 9 math. We've got, I'm going to try it without a calculator even, see if I don't bugger it up. 30 times 8 is 240, plus 20 times negative 10 is negative 200, equals 30 times negative 5 is negative 150, plus 20 VF. Another sort of weird mistake students make is sometimes people will combine these two things and they'll say, hey, look, that's negative 130 VF. Don't do that, right? You can't combine the negative 150 and a 20 VF because they're not like terms. So avoid silly algebra mistakes. Let's keep running the numbers. We've got 40 equals negative 150 plus 20 VF. We're going to add 150 to both sides, which is 190 equals 20 VF. I'm going to double check this on my calculator. I think I know what it is, but hey, let's not make a silly mistake. There you go, 9.5 meters per second. Final velocity for your 20 kilogram mass. So that's what collision questions look like when the two objects have sort of bopped into each other and they've bounced apart. Now what I would like to do is look at an example where something a little bit different happens after the collision. So let's try out this one. So here we're going to look for the final velocity, VF, if the balls after the collision get stuck together. So here's after number 2. This in physics, I call these the hit and stick questions. Let's imagine, and this would be a great day. Let's imagine that you had 50 kilograms of silly putty, which would be awesome. I love silly putty. If you've never played with it, you should go to the dollar store, I guess when COVID's all over, because this is not essential, but go to the dollar store and buy yourself some silly putty. It's fun stuff. You have 30 kilograms of silly putty at 8 meters per second, colliding with 20 kilograms of silly putty going to the left. It's the same before the scenario, before the collision, so you don't have to copy that down because that's the same. The only thing that's different is right here. After number 2, what if we roll these giant blobs of silly putty together and it just turns into like a big 50 kilogram blob? You'll see in some of the homework questions that you might have other things get stuck together, like cars, because sometimes cars get all tangled up together during collisions. Could be like football players or rugby players, like that picture of Nakai, where one person wraps up the other and they, in effect, become one big mass. Let's try this out. What's the final velocity of that giant big blob of silly putty? So you go to your formula sheet, and all you're going to find, all that you need, is that sigma pi equals sigma pf. And the cool thing here is we have the same before the collision scenario. So that looks exactly like the last example. 30 kilograms at positive 8 meters per second plus 20 kilograms at negative 10. Watch the negative because it's going left. Equals. Now what we're going to do is we're going to add the masses together, the 30 and the 20, because they're stuck and they've become this giant 50 kilogram blob. And we want to know what that final velocity is. So it's kind of cool, right? Like algebraically, there's one less term on this right-hand side. Should be a little bit quicker with the math. I think we said that left-hand side was a 240 and a negative 200, so it was 40 equals 50 VF. You'd be amazed how many students at this point, to solve for VF, will divide both sides by 40. And hopefully, just like I did there, that gives you pause, where you're like, what? Why would you divide by 40? If you're going to solve for VF, divide both sides by 50. So again, don't make silly algebra mistakes. We also want to make sure we catch our 2 to 3 sig figs. So 4/5, that's going to be 0.80. Make sure you get your 2 sig figs. Meters per second. There's your final velocity. So that's the hit and stick kind of question. I personally like those because you only have that one, the one term on the right hand side. Just a little bit quicker when you get to the algebra piece. So that's it for the lesson. That's actually it for chapter 5. I will make one more video just with some review. We're going to do a little Mythbuster style question with collisions, but I'll make it a separate video because it doesn't matter for right now. And this one's probably long enough. But you made it to the end of chapter 5. Congratulations. Well done. You did it watching videos. I'm proud of you. That's actually really hard. I don't envy you. I wish we were in class together. So give the collision questions a try. They're out of the textbook. They're on that chapter outline. If you have questions about this lesson or questions about the homework, please join me for one of our Zoom meetings. I'd love to chat with you and do some physics. Or fire me an email if it's something I can answer via email. Or fire me an email and we'll schedule a Zoom session to chat about a specific concept or question. I'm happy to do that for you. So give the homework a try. I think you'll like the collisions, and we'll chat with you at the next Zoom session. Have fun with collisions.